All right, I'm going to go through a curvilinear example that is it's going to require a few additional kind of tools of calculus as well as a little bit of vector understanding to solve. Um, the actual math isn't bad at all, but setting it up right is a little bit more involved than the problems we've done so far. And the prime reason for that is our position here is given as well, it's just y, y is a function of x. And then we're given a constant velocity as well. Now, what that's basically saying, well, the particle is definitely moving. It's moving along that path. And if it's moving along that path, then there are time dependencies, even though there's no time terms in the path equation itself. So I can still take time derivatives of that path. I just have to, in this case, use the chain rule in order to get the time dependency represented in the path. And that's where we'll start here. And all we're looking for is components in a Cartesian system, x and y, for velocity and acceleration at x is equal to 4. And incidentally, at x is equal to 4, if we put 4 into the path equation, we get that y is equal to 4 as well. So at the point we're interested in, x is 4, y is 4, and the velocity is constant, so it's always 4. So starting with the position equation, we need to take the time derivatives, and we do that with the chain rule. So as a reminder, the chain rule, and just I think I've already mentioned this, but just to repeat, I said that you take derivatives of vectors using the chain rule. I had the name wrong there for that example, which was I think the first day of class. That was the product rule, not the chain rule. Here we're using the chain rule itself. Incidentally, we are also going to be using the product rule in this problem, but here this is just the chain rule. Which basically, this is just kind of a rule of expansion. If you've got, you're trying to take the time derivative of a function that's given in terms of x and y, so in this case y is a function of x, what you can do is just write your expression out by kind of expanding and adding this dx term. So I've still got the d dt in those two terms, but what this is doing is now I'm taking a derivative of the function with respect to x, which I can do, and this term dx dt, well, that's velocity of x. So this expansion by adding that dx term top and bottom lets me take the time derivative, and then since I'm adding this dx dt term, I've got the time dependency. I'm adding that into the process as well. So this accomplishes everything that we want to do. So for this problem, I'm just writing it out kind of fully, ddt of the right-hand side and the left-hand side. And then I'm expanding both using the chain rule. And there are sometimes if you've got time dependency on one side of the equation, you may only need to use the chain rule on the other side. Sometimes you need to do it on both, and then sometimes you'll have time dependency in the path equation itself, and you don't have to do this. The problem I worked on Monday at the end of class was a case where we didn't have to use the chain rule. So we're taking the derivative with respect to y of y squared times dyt, which is velocity in y, or y dot in the dot notation. So we get the one side of the equation, and then the derivative of 4x with respect to x times dx dt, which is velocity in x, gives us the other side of the equation. So that is a functional relationship between the velocity in x and the velocity in y. Still can't solve that for anything useful with the information given, but we can drop down to the, we know the magnitude of velocity, which is the components of x and y combined vectorially, and that's done through v squared. Well, it's v is equal to vx squared, vy squared, summed, rooted. Dot notation. And now here we're going to apply some of the conditions that we do know, which is values for x, y, and velocity. And what I'm basically doing is from my velocity expression at the top here, top of the screen right now, I know that x dot is going to be, just take that 4 to the other side, I'll have 1/2 y times y dot. So I plug that into my Vx term, and then my Vy term is still just Vy, or y dot. And now in that, I know V is 4. I know Y at the time I'm interested in, or position I'm interested in, is 4. I can solve for Y dot, which is the velocity in Y at x is equal to 4. And that just comes out to be 1.79. And once I have that, I can go back to my velocity relationship, which again now is at the top of the page, and solve for x dot. I've just got 2 times y dot, so 2 times 4 times 1.79 divided by 4, and that gives me x dot of 3.58. Now, we need to take time derivatives to get to acceleration, but I'm going to take a little aside here and talk about the angle of the motion with respect to the Cartesian system. And this is actually going to be necessary to solve for the acceleration, but with the velocities solved for, we can find the angle, so I'm just going to show it here. It would be often be asked in a problem like this to find the angle of the velocity, and this is how you would go about that. So on the path, and we've got the path plotted there in blue, and this is roughly what this motion would look like. It is a second order function, and it passes through the point 4, 4. But I've just got the velocity at some point on the path. First off, you can note that velocities are always going to be tangent to the path. That's a good thing. That's a useful thing, and we can do a lot with that information. And since velocity is tangent to the path, or not since, but we need to relate it to something if we want an angle. So let's take the angle to the horizontal, which I've got in there as theta, or theta. So this is the angle between the velocity vector and the horizontal, or the x-axis, or the I unit vector, all the same thing. And basically, well, there's a few ways to do this. You can work directly with the velocity now that we've got the components, but even if you didn't have the velocity components, you could still find the angle just from the path equation. And that is using the fact that the angle of the tangent line, well, the tangent line is the slope of the plot. That's kind of the definition of slope, is the slope of a line tangent to a plot at a given point. So if we can find the slope, then we can find angle theta. So in this form here, this drops straight out of, this should be like calculus 1, or maybe even pre-calculus, definitely calculus 1 though. If you can take the derivative of y with respect to x at a point, that is the slope. That slope is the tangent of the angle, so you take the arctangent and you get the angle. In this case, the slope is 1 over root of x. That's the derivative of our path. And at x is equal to 4, we get a value of 1/2, and the inverse tangent of that is 26.6 degrees. Now, since we've got velocity terms, we can look at it that way too. We've got the velocity vector, it's tangent to the path along the diagonal. And we have solved for Vx and we have solved for Vy. Same thing, take the inverse tangent of Vy over Vx and we get the exact same angle, of course. Now I'm gonna move on, but I will say that with everything that's kind of on the screen right now, at the very beginning of the problem, before I do anything with the kinematic equations, I can use the first approach, taking the inverse tangent of the slope, to find the angle. Well, in the vector plot, if I know magnitude and I know the angle, well, I know the components of that vector. So I could actually solve for Vx and Vy without going through the steps of setting up the kinematic equation and taking the time derivative. I'm going to need that step to solve for the accelerations anyway, so it wouldn't make a lot of sense, but just be aware that you can do that. The vectorial relationships and the calculus relationships, those are going to be in place, regardless of the problem. There aren't, the better you understand those relationships as opposed to a specific solution sequence, the more robust your kind of tool set is for solving these problems. So anyhow, we'll go back to where we were at. And now we're taking the time derivatives of velocity to get acceleration. And here's where the calculus gets just slightly more involved. Still nothing crazy, but basically we're still applying the chain rule. But in this case, things are, well, there's a few things going on. So first off, I've got the velocity equation there at the top. And not that. Velocity equation. There we go. Right there. And taking the time derivative of both sides in the next step. And from that, on the left-hand side, we've got a time derivative of x dot, where x dot is the time derivative of x. So that's already time dependent, and I can just take the derivative directly. The derivative of basically velocity would be acceleration, so x double dot in this notation. On the right-hand side, we've got y, which is time dependent, but has no time expression in it yet. And we got y dot, which is time dependent, but does have a y expression. So we got basically two functions there. We got y and we've got y dot. They're separate functions, but they're both time dependent. In order to take that derivative, we have to expand that with the product rule. And the product rule basically means you got two functions that are dependent on a variable side by side. You take the derivative of the first function, multiply by the second function, and then you add the first function multiplied by the derivative of the second function. That's the product rule. So when I expand this out, I'm going to take I've got y times the derivative of the second function. Derivative of y dot with respect to time is y double dot. And then I take the second function as is, y dot, times the derivative of the first function with respect to time. Y, to take dy dt, or rather, dy dt, where y is literally just y in this case, well, you're using the chain rule again. Exact same thing. And that's done over here to the side. Right there. And since dy dt is just 1, all that we've got left out of that is the term y dot. Plop that into our expression and we get the full equation for acceleration, which is, in this case, the relationship between x double dot and y double dot, Vx and Vy. Now in this case, down here, either one, same expression, we know y at the point of interest and we know y dot at the point of interest because y was given and y dot, we solved that in the first part of the problem. But in that equation, we have x double dot and y double dot. They're related, but they're both unknown, so we do need another equation in order to solve this the rest of the way. And that other equation has to come from the vectors themselves in this case. So let's look at that. And this gets, there's a lot going on here. So let me just kind of go through a couple of points of interest first. Points of information, maybe. If the velocity is constant, then acceleration in the direction of velocity has to be equal to 0. Now, velocity being constant, the magnitude of velocity in this case, that is a product, or that is a resultant of the problem statement. We're saying that the velocity has a constant magnitude of 4 meters per second. Now, the vector of velocity is not constant because it's changing direction. As we go along that path, there is, at some instant, the velocity is going to be tangent to the path with magnitude 4. Here, at next instant or some point in the future, it's going to have the same magnitude, but now the direction is different. Vector is magnitude and direction, and acceleration is something that changes magnitude and or direction. So in this case, the accelerations are only causing change in direction, but they have to be there. But since the magnitude is not changing at any instant, the component of acceleration that lies along the same direction as the velocity, tangent to the path, has to be 0. If that were an acceleration vector that did not equal 0, then velocity would change. It could not be constant. That's just a definition of velocity and acceleration. If you have an acceleration in the direction of travel, the velocity magnitude is going to increase. And we know it doesn't increase. So the portion of acceleration, the vector component that lies in the tangent path, has to be 0. So if we can come up with an expression for that vector component, then we've got the extra part that we need to solve the accelerations. All right, so we're saying since the direction of V does change, the vector A cannot be 0. There has to be some actual acceleration. It's just that the component parallel to the velocity has to be 0. If the component parallel to the velocity is 0, then the full magnitude of the vector has to be 90 degrees from that. That's an important concept in and of itself. If you're breaking a vector down into two perpendicular components and one of them is 0, then the full magnitude is perpendicular to it. That's just code of a vector identity, essentially. So what that gives me is a direction for the magnitude of velocity perpendicular to, or I'm sorry, a direction for the magnitude of acceleration, which is going to be perpendicular to velocity. So let's draw that out and see if it makes any sense at all. So on this plot, I've got velocity. That's my x direction. Y directions, as you would expect here. And I've drawn in purple there the acceleration vector perpendicular to the velocity vector. And then in yellow, I've sort of penciled in the components of that vector, which would be ax and ay, in the Cartesian system. And then what I'm doing in the two pink vectors here, which would be that one and that one, those would be the components, respectively, of ax that is projected along the velocity vector. And then the component, that's that one, and then the component of ay that is projected along the velocity vector. So all I'm doing is taking two known vectors. Well, they're not known, but the directions are known, ax and ay, and I'm projecting them onto the velocity direction. Well, the magnitude of the vector component of acceleration that lies along the velocity vector has to be equal to 0. So that's what I'm writing out right here. The components of ax in line with velocity has to be 0. Or I'm sorry, the component of ax in line with velocity plus the component of ay in line with velocity has to be equal to 0. And then we know the angle of velocity relative to direction x, because we found that up above as 26.6. And then through sort of some right angle similarities, we've got that angle theta carries through the problem in other locations, which are shown there. And then just breaking the ax and ay vector down into those two pink components, we get ax cosine theta plus ay cosine theta is equal to 0. And let me make the connection here that ax cosine theta, let's see, that work. Ax cosine theta is that component, and ay sine theta is that component. All right, so now we've got another, and since theta is known, ax and ay are the only unknowns there. And now, let me, well, I never wrote this, so I might as well. Let's just say in the dot notation, we have x dot, or x double dot cos theta plus y double dot sine theta is 0. That's that. And we've got, we can take the velocity or the acceleration equation that's at the top of the page there and plug in what we know. We know at x is 4, y is 4, and we got the velocity there, and y is known. That gives us ax at x is equal to 4 in terms of ay. And then we plop that into our vector expression that was just found. And now the only unknown is y double dot, which we can solve for as minus 0.64. And x double dot is 0.32. So a lot going on in this problem. Just to kind of summarize there, what we used for, in terms of calculus, we're looking at the chain rule and the product rule in order to take these slightly more complex time derivatives. And then in terms of the vectors, we looked at the the fact that you can find an angle between a tangent path and the horizontal with that expression. Then we looked at the breakdown of the velocity vector along that angle here. And then last little bit, we were just using information from the problem to show that when your magnitude of velocity is constant, then the acceleration component in line with the velocity has to be 0, and you can break down the acceleration vector into components into a useful form to highlight that. Now, we're going to, next week, most likely, we'll start looking at the normal tangential coordinate system, which actually kind of uses a lot of the information from this problem to just define a new coordinate system that takes a lot of this into account and sort of simplifies things for motion that is along a dedicated path. So we'll use a lot of this information over and over again, but primarily the little bit of vector manipulation is important, and then of course the use of the chain and the product rules to take the time derivatives.